Where are you at? Oh, it's 12:30. Oh man, it's crazy. All right, let's get started. Lord, thank you for bringing us together this afternoon. Pray that you would help us to just be present today, to have the energy that we need to finish all the things that we need to do. Not get discouraged, but to stay positive and to just be here. In your name we pray. Amen. Okay, everybody's. So what are we doing today? First, we're waiting for this to turn on. Then when that turns on, then we'll be okay. But we're gonna do some stuff. You guys have stuff on your tables, right? We'll do that at the end of class once we get through some other things, right? But today is gonna be about some more stuff about linear momentum, right? So, because I didn't prep for this yet, we're gonna have to. I'll pop up and pull everywhere, and then we will do our normal thing. All right, so equations. Yeah, seems like there's a lot of equations, right? Seems like there's a lot of equations. Don't worry about really memorizing. Thanks. Don't worry about memorizing equations. What I want you guys to worry about, I told you, when we get the quizzes and things, we're going to have an equation sheet attached to it on the back end. Okay, so don't feel like you need to memorize all these things, right? In the real world, if you ever need these, you just need to know where to look for them. That's the important thing. You need to understand how to use all the different equations, right? And right now we've got three different methods in our toolbox. We've got Newton's second law, which is sum of my forces is equal to mass times acceleration. We've got work and energy, right? So the amount of energy that we have at state one minus the work that it takes, or sorry, plus the work that it takes us to go from state one to state two is equal to the amount of energy we have at state two, right? Or if we have conservative forces acting on our system, we have the amount of potential energy at the beginning plus the kinetic energy at the beginning is equal to the kinetic energy at the end plus the potential energy at the end, or conservation of energy as we typically call it, right? We also have momentum and impulse, and we haven't done too much with that. We talked about collisions, right? And that's when it's most applicable. But remember, when we have impulse and momentum, we say that the momentum at the beginning, right, at the first state, plus the sum of my impulses. And what are my impulses? Well, impulses are forces that happen over a very short amount of time, right? So plus the sum of all my forces times the time that it takes for us to apply those forces, right? Which is typically given to us as 0.1, 0.2 seconds. Think about like when a hammer hits a nail, right? That is a very large force that spikes over a very short amount of time, right? It's there, then it's gone instantaneously. Okay. So we're going to sum all those forces, delta t, and that's equal to my momentum final, right? Now the difference here is that when we have microphone's freaking out, so this lecture quality might not be great. Apologize if you're watching it later. If you're here in person, then it's not going to be a problem. So if we have conservation of momentum, what does that mean? Well, that means that the two things that are hitting each other are applying an equal yet opposite force on each other, right? So we can cancel out that impulse term, and momentum is conserved. Is momentum always conserved? No, momentum is not always conserved, and we'll see some examples of that later. But for particles, it's pretty much always conserved. All right. Do you guys have any major questions that you want me to answer right now? Just feeling okay? Everybody doing all right? Maybe stop asking. Yeah.
So we're going to discuss the wind turbine thing.
Yes, we are. Very, very next thing. Zach, please stop stealing my thunder, man. This is ridiculous. All right. But yeah, we are. We're going to talk about it. So these are the things that are due, right? At the VOT research essay, homework 3, exam 1, which I've called A Curious Existence, and Learn Smart, chapter 15. So this weekend, we've got our VOT research essay. We'll talk about that in just a second. Homework 3 is due on the 15th, which is not a Sunday. Not a Sunday. The day before the exam, which is a week from Friday. Okay? So this is due on a Thursday. And why? Because I think it would be beneficial for you to have done the homework prior to seeing stuff on the quiz or the exam. Remember, exam 1 is a combination of quiz 1 and exam 1, right? So it's worth a total of 65 points, which is not the most of any of the assignments that we have here, right? It's less than 3 Learn Smarts, if you want to think about it that way. I'm not telling you this because I don't want you to take it seriously, but I don't want you to psych yourselves out and think that the name exam carries more weight than it actually does. Okay, what's it going to look like? It's going to look very similar to the homework, right? It's going to cover everything up until Tuesday of next week, or sorry, Wednesday. Today's Wednesday of next week, right? Wednesday of next week, if everything goes according to plan, we'll have a little bit of time. Part of the lecture we can use for, you guys have review questions, right? So if you have any specific questions, that's a great time for us to go over them, okay? And then a Learn Smart due for chapter 15, which is the stuff that we will start to cover the week after the exam, right? So it's not exam eligible. You guys have any questions on the stuff that's due in the next couple weeks? So let's talk about the VOT research essay, right? So it says here the purpose of this section is to describe, right? So I like to think of this project as multiple sections of the same project, right? So ideally what you're doing is you're compiling a prospectus, right? You're coming up with your business idea, right? The first part was, what is my product plan, right? Tell me a little bit about your organization. Who do you plan to partner with? How much basically does it cost? How do you benefit the area that you want to put it in? This is going to flesh out all of that stuff a little bit more and point you towards your design, right? And so this section, you need to describe your preliminary design. Now you're still working individually for this, okay? Because the idea is that after this point, you'll all have an idea for a preliminary design. Then when you get into your CLC groups, you guys can, flip a coin, argue, fight to the death to figure out which one of the designs you want to use, right? It's up to you guys. All right, so to this end, you will need to research a sand filtration system, right? So I'm telling you that the way that you're going to filter the water is through a sand filtration system. So you're going to look up sand filtration systems. You're going to be sure to discuss the pros and cons of the various types of sand filtration systems, right? So there's more than one flavor of sand filtration system. Tell me the benefits and the disadvantages to each of those, right? Your research should drive the selection of a sand filtration system. So based off of your research, tell me the reasons why you've decided to choose the one that you're going to go with, right? The type of filtration system will necessitate a pump for getting water from the source to a cistern, right? So typically, the way that sand filtration works in general is it's gravity fed, right? So it takes some water from a cistern, feeds it down into your filter, and then your filter then will either save it or pump it out directly, right? So we need a pump to take water from a source and dump it into the top of our sand filtration system, basically, right? Or into a bucket that feeds our system. So you need to figure out, based off of the filtration system that you've chosen, what kind of pump you need to use, right? So how do you size your pump? The pump is going to drive your power requirements, right? So your VAUT is powering the pump that's going to bring your water to the filter, right? So once you figured out how big of a pump you need, then you know how big you need to make your vertical axis wind turbine, right? Because once you figure out the pump, you know how much power you need. That will in turn determine how big your VAUT needs to be or how much power your VAUT needs to supply. According to unwater.org, nearly 1 billion people do not have access to a safe source of drinking water. Every day, people die from polluted water-related illnesses. For this assignment, you will research gravity-operated water filtration system and a VAUT design to produce electricity to operate said system, and write a short paper about your findings. Right, remember your village that you are supplying water to is roughly 200 people who each need a minimum of a half gallon of drinking water per day. So that's your target with your sand filtration system, right? Research the requirements for a gravity operated filtration system. Select gravity operated filtration system that will meet the needs of the village population. Research should include a basic sand filter design and a maximum height of the cistern that you will need to pump the water, and the minimum pump requirements, including pump flow capacity and pump power requirements. And we don't want to over-engineer, right? So don't just say, well, I'm going to get the biggest pump that I can, right? Because then you're going to have to over-engineer your VAUT, right? And the whole point of the VAUT overall is to have this nice portable source of power generation that can be moved from place to place very easily. So you don't want it to be extremely large, right? You just want it to be large enough, right? So determining how big of a pump you need is really important. What do you guys think would go into determining the size of the pump? What do you guys think? So definitely the height, right? That's going to be a major consideration, right? You need to make sure that you can pump up to a certain height, right? You also don't want it, it's also the flow out, right? You don't want it to fill, to overflow your cistern, because then you're just wasting that water, right? So you need to figure out how much water you need to supply over a certain amount of time to fill your cistern while it's also emptying into your sand filtration system, right? So each of those things has a flow rate associated with it, right? So you can figure out, it's basically a related rate problem, right? If you're filling the bathtub with X amount of water and it's draining with Y, how much do you have saved up inside the tub, right? You guys have any questions on this? There's a rubric associated with this, right? Please read it. Make sure you familiarize yourself with what's being expected, right? But in general, I'm looking for you guys to really hone in on making logical decisions about your your gravity filtration system, your sand filtration system, right? So make sure that you don't just say, oh, I picked this one, right? Please make sure you have reasons. Go in depth into the pros and cons. There's a lot of research out there, right? In terms of calculations, make sure that you look into the pump calculations, right? They're readily available online as well. Right. Any questions? No. There's a little bit more. Once your water filtration system requirements have been determined, research what your VAUT design would need to be to meet those requirements, right? So now that you know how big your pump is, then you can get to designing your VAUT. So you can figure out these things, right? Doesn't have to be complete, right? It doesn't have to be like, this is the design, here's some SolidWorks models and everything. What we're doing is we need to determine how large it is, right? What materials you want to use. So you want to be using materials that are readily available in any place so that they can be repaired easily. So like, you don't want to use anything that's too exotic. You want to make sure that it's easy for people to get it, because the idea here is that you're setting up this vault in this remote location, and then you're going to leave and you're going to teach the people of the village how to maintain it, how to operate it, right? And they need to be able to repair it on their own without having to call for help every time that they need it. Use components that in the event of failure can be replaced easily. Design process is clearly outlined, right? So you have to clearly outline your design process. Specifically, it's really, this is assembly instructions, right? So how do you assemble it? Make it clear so that anybody can read it. Any repair, right? We talked about this, of the turbine could be accomplished without specialized tools or training. The turbine needs to be lightweight and modular, right? So it needs to be a lightweight and needs to be able to move around the village, right? If part of the year wind comes from the north, but the other year the wind, other part of the year comes from the east, they need to be able to shift it to better locations. This is supposed to be 300 to 500 words. I'm not a stickler on word count, right? Make it as long as it needs to be, right? As long as it's not like a novel, as long as it's not Stephen King's seventh book of the Dark Tower novels, right? We should be okay, which is, if you guys know, that's a long one. Right, you should detail the design you have chosen and cite 3 to 5 sources, right? So you're going to need to cite sources on this one, right? In-text citations. Right. We have any questions now? Again, look at the rubric and let me know if you have any questions regarding the rubric itself. Remember, the rubric is the grading criteria, right? So make sure that you're hitting all the notes in the rubric, right? Make sure you're hitting all the notes in the rubric.
So I guess what parts are we actually, for the designer actually putting in there? Like the anchor, what kind of generator or?
So just the turbine. So don't worry so much about the generator. Assume that your vault interfaces with the generator perfectly. Okay. What you need to worry about is essentially what geometry you're going to put your fins, your blades in, right? How do you want to align your blades? How many blades are you going to use? Right? What is it going to be made out of? Okay. This is, remember, the only calculation driving this part of the design process is I need to ensure that I get this much power. How are you supposed to determine that, right? Great question. How are you supposed to determine that? Well, you should have picked a region in the world where you know what the average wind speed is. So assume that you are operating under the standard wind speed of said region, right? Assume that that hits the edge of the turbine blade, and so you know the distance away from center. So guess what? The velocity times the radius gives you the angular velocity, right? And angular velocity times torque is going to give you power. How much power do you have? Well, you need to understand how much force is being applied at the edge, right? How do we figure that out? Well, you can figure that out from wind speed equations and multiply it by the radius of the blade, and you'll get the torque. Right? So torque times omega gives you power. That's how much power you're generating. It's the same as the electrical power that you need. Well, you should be producing as much as you need. Right? Does that make sense? Ish. There's going to be some legwork on your guys' part, right? There's nothing in the textbook that has canned equations for this, but there is a lot of research out there, right? And so we've done this project enough, and I know that you guys can find what you need on the internet, and please cite everything that you use, right? So if you find a specific equation, right, make sure you cite it in your text. All right. This is the lead up, right? Because the other parts after this are actually a little bit, I think, are a little bit more fun, specifically the build and test at the very end, right? But we need to get through this stuff first. All right, you guys have any other questions? If you think of anything, remember I've got office hours 3 to 5 today. I've got office hours for Friday from 3 to 5 as well, none tomorrow, right? So, all right, so we're gonna continue. I know we talked a little bit about topic 3, the end of class on Friday. We're gonna recap some of that stuff, talk about how to derive Newton's laws and momentum for systems of particles. We'll talk about kinetic energy from systems of particles, and then we're going to do our Expecto Momentus Linearum thing, which is the reason why you have ball launchers and pass cars on your tables. And we'll consolidate so that we have, since it looks like we have an even number today, we'll consolidate so that we just have 2 people using each setup. So, where did I put it? There it is. What is topic 3? Well, that's the kinetics of systems of particles, right? So we're going to do everything that we just did for a single particle for a system of particles. This is kind of a lead-up topic. This is going to lead us in directly to rigid bodies. Some of the things that we talk about in this topic are the basis for why we can talk about rigid bodies in the way that we do, right? So we're going to solve kinetics problems involving particles by applying Newton's second law. And we're also going to solve them by applying energy and momentum methods, right? So all of the things in our toolbox. Right, we talked about this, right? We need to understand where the center of mass for our system is, because we have a system of particles. It turns out, right, the punchline is that we can discuss how a system of particles moves by tracking the center of gravity, right, or the center of mass of those particles, of that system. The application of work and energy principle and impulse momentum principle to a system of particles will be described later, and we'll talk about analysis methods for variable systems of particles, and that'll be Friday's class when we talk about that. And that's basically the basis for fluid mechanics. So often as engineers, we need to analyze the dynamics of systems of particles. And we'll see a couple of applications today through the problems that we do as to why this might be important. So here we are, right? These are the math heavy ones. This is where, again, we're going to go through the derivation. I don't expect anybody to replicate the derivation, but I want you to understand where it comes from at the very least, right? So Newton's second law for a particle in a system of n particles, right? So we've got n particles, right? So what is this equation, right? Well, this is the external force Fi plus the sum of all of my internal forces, right? So this system of particles, think of it in terms of chemistry, right? When you have a molecule, right? Each of those atoms in that molecule is exerting a small amount of force on each of the other ones, right? And this is like a system of particles, right? When you have all these different things doing it, right? But all of these forces here, right? These are internal forces. And we can rewrite this as the cross product here of Ri times F1. Well, what's Ri? That's the distance vector here. Cross F1 plus the sum of all of the, what is this? This is Newton's second law, but for rotations, right? This is going to describe the moment or the torque. The moment, the torque on a system is R cross F. Okay? The system of external and internal forces on a particle is equivalent to the effective force of the particle, right? So what this is saying is that we can say all of the internal and external forces, we can consolidate them into a single force that we can call the effective force, right? So I can do that, right? And the system of external and internal forces acting on the entire system of particles is equivalent to the system of effective forces, right? So again, in this case, I can rewrite all of these forces as a single force, right? My effective force. In this case, I can rewrite all of the forces acting on my system as a single effective force, right? And this is important because we can sum it over all of the different particles that we have, right? And if we sum this over all of our different particles, right? Notice we still have this rotational equation here. This is for translation, this is for rotation. And if we do that, well, the internal forces are equal and opposite for our system of particles, right? P1 has the same force acting on P2 as P2 has acting on P1. So if they're equal and opposite, then they sum to 0, and then we are left with this. What is this? Well, that looks like Newton's second law, right? This is just the sum of all my external forces is equal to the sum of my masses times my accelerations, right? So if I have 3 particles, right, this is the sum of all of my external forces. In this case, I've got 2. That's F1 plus F2, right, is equal to the sum of mass 1 times the acceleration of particle 1 plus the mass 2 times the acceleration of particle 2 plus mass 3 times the acceleration of particle 3. So what we're saying is that if you have a system of particles, right, the sum, the whole is equal to the sum of the parts, right? So you can take into account each and every particle that we have here, and by pushing one, because it's a system and it's linked in some way, the others will move, right? So the easiest way of thinking about this, right, is if you had a cloud, right, cloud of vapor or gas or whatever, it's a cloud of particles, right, and you blow a fan on it, right? I don't have to hit every single particle in that cloud to get it to move. I just have to hit some of them, and the whole cloud will shift and move, right? It's a bad example because that's going to diffuse out and it's going to be wonky, right? Here's another example that's a little bit better. Can't I just say that a solid object like the table in front of you is a collection of different particles that are, because it's a solid though, it is bound to be a certain shape that will not change, right? If I push one specific particle on that table, the rest of them will also move, right? Because that's the way that solid objects work, right? If I push this here, this is going to move, right? The whole thing is going to move, not just that one particle. This is what we're kind of getting at, right? When you have a system of particles, right, and you have a system of particles, you can reduce a rigid body to being a system of particles that are all forced to move together, right? And that's kind of where we're headed. And look what happens, right? If I have this particular object here, right, this clicker, and I'm pushing here, right, it wants to translate, it wants to move that way, but it also wants to rotate, right? So now I've got 2 equations that I have to deal with here, or 2 sets of equations, right? I've got the sum of my forces and the sum of my moments, or torques. What about linear and angular momentum? Yeah, Zach.
On the last slide above, the grid diagram top right, like, probably equal, like, 2 versus 3 particles, or,
So remember, this is basically the free body diagram here on the left, and this would be the kinetic diagram on the right. All right, so if you look at each of those particles, right, is there an external force on all of them? No, there's only on F1 and F2, so there's no force here. But because this is a system of particles, they're all going to move in a certain way based off of these 2 things having forces, right? The idea of a system of particles is that there's some internal forces that are connecting each of these particles, right? There's some internal force, but for our applications here, the internal force from P1 to P2 is the same as P2 to P1, right? They're just in opposite directions, and so they will cancel. So our internal forces end up canceling, and that's why we're left with these 2 equations. Unlike a single particle, though, the reason we have this rotation is because this whole group of particles could rotate about its the center of gravity or the center of mass of that system of particles. Okay? Does that answer your question? Anybody else have any questions?
So the reason all the internal forces cancel out is because the external force has to act in some relation to the center of mass, right? So there's always going to be some sort of thing pointing towards the center, or?
So it's a good question, right? So let's say for this particular system of particles, that looks like the center, right? So basically right in the middle of all three. Okay? You know this distance. You know this distance, right? And you know this distance, right? There's some force that's acting on these two. And remember, these also have internal forces that are equal and opposite. And I've drawn those not that great, right? But these have equal and opposite forces, right? Which keep them in relation to each other in some way. And because they're equal and opposite, they cancel, right? And so what we're really doing is we're tracking how that center of mass moves in space. We're less concerned about these particles shifting away and the center of mass changing where it is in relation to them. We're more concerned of where is that center of mass of that system of particles at any given time, right? And so for this, right, you can kind of see right here. If I was to push here, right, so imagine I just had a beam connecting the center of mass to point 1, right? If I'm going to push down like this, it's going to cause a rotation around it, and it's going to want to move a little bit to the right because that's not perfectly down. It's not perfectly perpendicular, right? You've got an X and a Y component here. Same deal with 2, right? This is going to cause some rotation, but also some translation of this point, right? So it's going to cause this to move this way, but we're also going to rotate our particles some more, right? Which is why we have our mass times acceleration, because those two are moving, the third one's got to move some way, okay? So as a whole, right, we are essentially going to want to track how the center of gravity of a system of particles moves. And that leads directly into how we treat rigid bodies, right? Because if you think of a rigid body as a collection of particles that are bound together and cannot change their shape, then we can just track the center of gravity and we would have a good approximation of how it's moving, right? That kind of answer your question, or?
Yeah.
Okay. Anybody else? All right, so let's talk about linear and angular momentum. All right. So we talked about linear momentum, and there's a homework problem that you have linear momentum is mass times velocity, right? So if you had a system of particles, we can do the same thing. We can calculate the total linear momentum of a system of particles by adding all of the momentum from each of the particles, right? So again, you're assuming that in its most basic state, right, in its most basic state, it's not always the case, but it can sometimes be the case, especially when we have gases, a gaseous flow, right? That each particle might have a different velocity. Now, in a rigid body, that's not going to be the case, right? If I throw this at you, the translational velocity of the entire thing is the same, right? Hopefully, otherwise it's going to stretch and bend, right? So linear momentum is m, the sum from I is equal to 1 to n of mi vi, right? So if you want the total linear momentum, L, of a system, you just add up all of the linear momentum from each of your particles, okay? right? Remember, if we take the time derivative, this is just, that's equal to the force, right? So the sum of my forces is the time rate of change of my linear momentum. Okay. That's great, and that doesn't seem super helpful for anything, right? Because typically, we haven't done any problems where we even care about what L dot is, right? Well, this comes into play when we talk about angular momentum, right? Because we haven't really talked about angular momentum yet. But remember, angular momentum, remember from the video we watched, right? Angular momentum depends specifically on wherever we're deciding to measure from, right? So if you're measuring from the center of gravity of the object, that's going to be a little bit different than some fixed point O. But let's imagine we have some origin, we call it O, right? And we're gonna measure our angular momentum from there. Well, what is our angular momentum? Well, remember, angular momentum, we remember the video, right, is our linear momentum times the radius, right, times the distance we are away perpendicular to wherever we're measuring from. So the sum of R cross M VI. Now, this is a very general equation, right, where we're going to have to do cross products to get it. And this will always work, right? You always take the cross product of vectors to get your answer. But if we break it down into x and y components, this then becomes R times M times V, right? Where R is my perpendicular distance away from the point O. This point O. So we can do the same thing here, right? Where we sum this up for all of our particles, right? And we'll take the derivative just like we did last time. And because it's, we have to chain rule it, right? And we'll end up with this as our relationship here. Well, that is important because as it turns out, the sum of my moments about point O, the sum of my torques about point O is the same as the time rate of change of my angular momentum. So there's a direct relationship between the two. Okay. There's a direct relationship between the two. Now, for systems of particles, it might not be obvious why we would want to use angular momentum, right? But we'll do a couple of problems where it helps us out in a very nice way. We can get some information about our systems that we're going to be talking about, these systems of particles, from talking about the angular momentum about the center of gravity or some other fixed point. What if we wanted to take it about the center of gravity, right? So R sub G meaning the distance we are from the center of gravity, right? Right, so you differentiate this twice. Hey, look at this. If you're tracking the center of gravity, the mass times the velocity of the center of gravity is actually equal to the sum of my mass time for each particle times the velocity of each particle. So hey, if you're calculating this for the center of gravity, you're doing it for the whole system of particles, right? That is a powerful thing, right? Because same deal here. Mass times the acceleration of the center of gravity is equal to the force on my entire system of particles, my effective force. It's a big deal, right? Because that means by tracking the center of gravity, we can describe how the entire system of particles is moving. Now, again, I keep saying things like, well, if you have like a system of particles that are gases, right, they're going to diffuse. I think we all know that, right? If you had steam coming out of a pot on your stove, right, and you blew a fan on it, it would disperse, right? These equations aren't going to tell us anything about that. And we are not going to do anything with that in this class. We are going to focus simply and strictly on rigid body mechanics after this point, because that helps us most with mechanical engineering stuff, right? So angular momentum about the center of mass, right? Well, hey, look at this. This is my origin, right? This is my global coordinate system. And then I've got my system of particles that has a center of gravity here at G. And I can figure out where particle 1 is with relationship to that, right? And so I can say that the acceleration of my particle, I, is equal to the acceleration of the center of gravity plus the acceleration of that particle I. We call it AI prime. And what is AI prime? Well, notice A, this is the total acceleration. And because it doesn't have the prime, it's referring back to this origin, right? So how do I look like I'm accelerating from standing here versus how do I look like I'm accelerating from standing here? Now, why do we have multiple accelerations for the other frame, right? For G. All right, so if you're on a train, right, and it's moving this way, right? This frame is moving with the train. If you're standing still, you're still moving with the train. But if I start moving in the opposite direction, right, I'm now distancing myself from this point G, right? It's the same idea, right? It's a relative acceleration. It's a relative acceleration. Centroidal frame is not in general a Newtonian frame, meaning that it is not fixed.
Do you mind if there are that slide?
Yeah, sure. Right, so remember, when you hear that there's a Newtonian frame, that means that it's fixed. What does it mean when it's fixed? That means that it can't move. Right, that means that it cannot move. Well, apparently, oh, it's still working. All right, so that means it can't move. A centroidal frame is not a Newtonian frame. The center of gravity can move in space, right? That's how we track motion of it, right? We typically measure it from some fixed point, right? If I throw this against the wall, right, I can track how this moves by tracking the center of gravity of whatever I've thrown, right? But that's part of it, I guess. So when we talk about a centroidal frame, we're not talking about something that's fixed. It's a moving frame. And remember, we talked about moving frames a little bit a couple weeks ago. What did we say about them? Right? Remember, that's the problem we did where the car was coming down the intersection and the other one was coming across. When we have moving frames, we need to talk about them in terms of relative position, relative velocity, and relative acceleration, which is the point. So we can do this, right? And the whole point of this, the punchline of this proof here is what? Well, it turns out that the momentum, the angular momentum of my center of gravity, right? If I take the derivative of that is just equal to the sum of my moments about the center of gravity. So what are we going to do? Well, we're going to want to track the center of gravity. How do we find the center of gravity, right? Hopefully in the statics class, right, we learned about doing centroids and all those things, right? Super fun. I tell my students in ESG 360, right, it's not, I don't expect you guys to memorize any of where those centroids are. They have tables for that. It's fine. But there are a couple that you should just know. Like, you know, where is the center of gravity of a rectangle, right? Or a square or a circle, right? A lot of these geometries, we can intuitively know where the center of gravity is, right? Especially if it's something that's made of a single material. Now you get into trouble where you have like things that are made out of composite materials or composite shapes, and then we have to do our tables and figure out, well, what's the center of gravity of part 1 and part 2 and part 3, and then we can add them all together and figure out where the actual center is, right? the moment resultant about g of the external forces is equal to the rate of change of the angular momentum. All right. So we can write our angular momentum about the centroidal reference frame, or about the centroid, as this, right? And again, this is the most general case. This is the most general case. And we can keep going, right? Because why? Because this is even better than the last solution. What does this tell us? This tells us that the angular momentum of G, right, as seen from O, is the same as the angular momentum if we were standing on the centroidal frame. So we don't need to worry about this centroidal frame business. We can measure everything from here, and we can get our momentum about G. Angular momentum about G of a particle, momenta, can be calculated with respect to either the Newtonian or the centroidal reference. Momenta is the plural of momentum. That is Dr. D's Greek word for the day, right? Like, rate, subscribe. What if we don't have any external forces, right? Well, if we don't have any external forces, then linear momentum and angular momentum about a fixed point O are conserved. So if you have no external forces, the rate of change of my momentum is 0, which means that my momentum has to be constant, right? So that's when we would have conservation of momentum. We didn't talk really about central forces. Central forces are those that are like something orbiting the Earth, pulling it back down to the center of the Earth, right? And in those cases, such as central forces, we can't say that linear momentum is conserved, but we, however, can say that angular momentum is conserved. We can extend this to the center of gravity as well of a system of particles. And if we do that, then we can come to the assertion, in this case, that our linear velocity is constant, right? Because mass is a constant, and if L is constant, then V has to be constant. And also that, in this case, our angular momentum about the center of gravity is constant. All right, we'll watch a video.
Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
For this video, we're going to be doing another particle kinetics example. However, instead of looking at a single particle, we're actually going to be looking at a pair of particles. And the more technical term for that is a system of particles. The example that we're going to be looking at is a pair of boxes, one sitting on top of the other. We need to give these labels, so I'm going to call the top one A and the bottom one B. And in this situation, we're going to have a force applied to block A that we're going to call P. And there's going to be some sliding that occurs between both block A and block B and the ground. So we need some coefficients of friction for those situations. So I'm going to note that we are assuming that in both of these contacts, the blocks are sliding relative to each other. So now let's look at the kinetic equation, which is simply the sum of the forces is equal to mass times acceleration. In the past, this was all there was. We didn't have to worry about anything else. But in this case, we have two separate blocks. So we'll say that the force applied to block I, where I can be anything, is equal to the mass of block I multiplied by the acceleration of block I. So this gives us two separate equations. We can also look at the sum of the forces over all of the blocks, and that would give us the mass of the total system multiplied by the acceleration of the center of gravity. This m here is simply equal to the sum over I of all of our particle masses. And this acceleration is the acceleration of the center of gravity, which is also called the center of mass. Now, this equation is not going to be useful in our situation. So if we had a situation where both of these blocks were moving together, say they weren't sliding, well, in that case, we would be interested in this acceleration of the center of gravity because the acceleration would just be the same for both blocks. But for this case, we're really just interested in looking at the individual blocks. So I'm going to draw two separate free body diagrams, one for block A and one for block B. Now, the first force that we can find here is this P that we defined. So P is just going to be pointing directly to the right. Now, P is what we call an external force. It is a force that has been externally applied to one of our blocks. Another example of that is going to be the force of gravity acting on A. Now, on block B, we also have the force of gravity, and this is still an external force. The other external force that we'll have is the normal force of the ground pushing back on B. And then also, since this is moving against the ground, we're going to have the force of friction acting to the left, since we're going to be opposing the movement caused by P. And that's going to be the force of friction acting from the ground onto B. So A is going to have two external forces, B is going to have three external forces. Now, we're also going to have internal forces. These are forces that are inside our system of particles. So A is going to have some forces that are acting on B, and likewise, B is going to have equal and opposite forces acting back on A. So the way that I'm going to write these, I'm going to say that there's a normal force of B pushing on A. So I can write that as normal of B acting on A. And likewise, there's going to be a friction force of B acting on A. These internal forces are going to have equal and opposite effects on the other object. This friction force that's pointing to the left on A is going to be pushing to the right on B. And we say that this is the force of friction of A acting on B. The normal force of B pushing up on A is going to cause some force pushing down on B. So we're going to have the normal force of A acting on B. Everything is nicely divided in I and J here. We don't have anything that we need to split. So first, let's define our coordinate system. It's pretty straightforward for this one. We can just say that I is pointing to the right and J is pointing directly upward. So that means this force P we can write as a magnitude and a direction. Magnitude of P, and it's pointing directly to the right, so that's I. Force of gravity here, we can write as a magnitude of m times g, and the direction there is negative j. It's pointing down. The normal force of B acting on A, I'm going to give this a magnitude of nBA, and this is pointing upward, so it has a direction of j. And then finally, our friction force of B acting on A is going to have a magnitude of mu AB multiplied by our normal. So this is mu AB multiplied by nBA, and this is acting in the negative I direction. So I'm going to write a negative I. So we have our two external forces, and then our two internal forces, the normal and friction between the two blocks. So next, I'm going to write the three external forces for B. So first off, we're going to have the force of gravity for B, which is going to be m times g in the negative j direction. And this makes me realize that we need to label what masses we're talking about. So the mass for A is just going to be ma. The mass for B is going to be mb. And then we have the normal force and the friction force of the ground acting on B. So the normal force is going to have a magnitude. I'm going to call that magnitude NGB, and that's going to be in the positive j direction. The force of friction is going to have a magnitude of this mu bg multiplied by our ngb, and that's going to be in the negative I direction. So that takes care of our external forces on B. And now we can write our internal forces. So remember that these forces need to be equal and opposite to their counterpart, which means that the normal of A acting on B is going to be a negative in BA in the J direction, which matches up with what we drew right here. And the force of friction of A acting on B is going to be a positive mu AB in BA multiplied by I. So now we're going to write the sum of the forces is equal to mass times acceleration for each block split into I and J components. So first, let's look at the forces acting on A in the I direction. And for this, we're going to have P, and we're going to have our force of friction, which is negative mu AB in BA. And this is going to be equal to mass times our acceleration. Now, we haven't split up our acceleration yet. Neither of these blocks should be moving in the J direction. There are no forces here that allow it to move in J. So our accelerations for both of these are going to be in I. So I can write that the acceleration of A is simply equal to the acceleration of A magnitude completely in the I direction. And likewise, the acceleration of B is just equal to AB in the I direction. And all that these mean is that we are not moving at all in J. So back to our equation, we're looking at the I component of force is equal to mass times acceleration for A. So this is going to be the mass of A multiplied by the acceleration of A, which we said was all in the I direction. So now let's look at the forces of B in the I direction. For this, we have the force of friction of the ground acting on B and the force of friction of A acting on B. The force of friction of the ground is going to be a negative mu bg in GB, and that was an I. For friction of A acting on B, this will be plus mu AB in BA. And all of that together is going to be equal to the mass of B multiplied by the acceleration of B. All right, so now let's look at A in the J direction. So our only external force in J is this MAG. So this is negative MAG, and then we have NBA also in J. So we'll have plus NBA, and we don't have any acceleration in J, so the right-hand side is just going to be 0. All right, our last equation is B in the J direction. For this one, we have two external forces. The force of gravity is negative mb times g plus this normal gb, and then our only other force is, again, this nba. So we have minus nba, and once again, there's no acceleration in the J direction, so this will be equal to 0. So now I just wanted to spend a moment to think about this from a mathematics perspective before we actually solve. And specifically, I want to look at the number of unknowns and number of equations. If these are the same, then we should be able to solve it. So right now we have 4 equations, and our unknowns are the accelerations, AA and AB, and the normal forces, NBA and NGB. So we have 4 equations, 4 unknowns, which means that we should be able to solve this. So starting off, low-hanging fruit, NBA is just going to be equal to MAG. And this actually moves into our other 3 equations. So next low-hanging fruit is going to be NGB. So between NBA here and the mass times gravity, NGB is just going to be equal to the mass of A times gravity plus the mass of B times gravity. Now that we have these, it's pretty easy to go ahead and plug into our I equations in order to find the accelerations. So to recap, we started off with our problem, understood what was going on with all the forces and the accelerations, so that we could write our free body diagrams for our individual pieces of the problem. Once we had the free body diagram, we went ahead and wrote out all of the forces in the coordinate system that we chose. So even though there were a ton of forces here, we could plug them in to the sum of the forces is equal to mass times acceleration for each of the blocks. And the individual equations weren't too crazy. Once we found some of these intermediate solutions, the final piece of plugging everything in to find the acceleration of A and B is pretty straightforward. So the hard part of this in my mind is keeping everything straight, is the accounting of all these forces. But if you draw them all out and recognize that the internal forces are going to have equal magnitudes but opposite directions, then we have enough information to go ahead and solve. So I hope you found this informative and that you're ready to solve problems with systems of particles.
Okay, so I'll pull that up in a second. But, right? A lot of this is going to boil down, or a lot of this is going to boil down to us determining we're going to boil down to. This one. All right. So I know you can barely see that. Please pull it up on your phone or your computer. Right. The small identical spheres A, B, and C, which can slide on a horizontal frictionless surface, are attached to three 200-millimeter long strings, which are tied to a ring G. Initially, each of the spheres rotates clockwise about the ring with a relative velocity of v rel. Which of the following is true? Which of the following is true here? Is it A, that the linear momentum is 0? B, that the linear momentum is positive in the x direction? C, angular momentum of the system is in the positive y direction? D, the angular momentum of the system about G is 0? Or E, sounds like someone's got a case of the Mondays. What's up, Zach?
So in the video, I was saying, you have a, so when you had a vector, you had a arrow of it, it was the same as if you had like a variable with a half thing.
Yeah.
Caret, I guess.
Yeah.
But sometimes you use like both at the same time, as if they were like a different thing.
So they're interchangeable. Typically, when you see like I hat or J hat, that signifies that it's a unit vector, which just means that it has magnitude of 1 in that specific direction. But if you have the arrow over it, that's the general notation for any other vector that might have a magnitude that is not 1. Question. Yes, please. Phone or computer. You can either text the Quizzard to 37607 or go to polleverywhere.com/thequizzard, or you can have the Poll Everywhere app on your phone and join 37607. That would be better. Oh. Now people can see the picture on the screen. Much better. So which one of these is true? One of these is true. Which one of these is true? Everybody? So, all right, so everybody will get it now. Did everybody get one in? Maybe, maybe not. All right, so let's go through them. The linear momentum of the system is 0. How do we define linear momentum, right? What is the equation for linear momentum? It's L is m times v, right? Remember, if you contract the linear momentum of the center of gravity, right, then you know the linear momentum for the entire system, right, based on what we said. So m times the center of gravity velocity is my linear momentum. You know that the center of gravity here is going to be this ring. This is going to be moving with v naught, so it can't be 0, right? The linear momentum of this system can't be 0. The linear momentum of the system is positive in the x direction. Yes. What's up? Well, if it was 0, then it can't. So not if there's a rotation going on. So think about this on the table, right? You're looking at it from the top and you're spinning like a fidget spinner in a circle, right? And you let it go. It's not fixed to rotate through that center, right? It's gonna climb on the table as it rotates, right? It's gonna kind of cone its way up. If V naught was 0, then you would have to be told that there's an axle or some sort of fixed point there, right? That it's constrained at the center of gravity, which it's not. It's free to move. The angular momentum of the system is 0. Well, remember angular momentum, what is it? It is m times r cross m times v, right? In this case, this particle is moving with v relative perpendicular to here, right? So it's going to be this distance, which is, we'll call it L, times v rel. The angular momentum is non-zero here as well, because we have v rel. All right. So the answer is B, right? And it's B because L is equal to m times v naught, and v naught's going positive in the x direction. It's not y. It's not in the y direction because there's no momentum. There's no linear momentum in the y direction. All right, so let's try one. All right. So we've got a 20-pound projectile. It's moving with a velocity of 100 feet per second. All of a sudden, it explodes into 2 fragments, one being 5 pounds and one being 15 pounds. Immediately after the explosion, the fragments travel in the directions theta A at 45 degrees and theta B at 30 degrees. Right, so we know these 2 angles. We want the velocity of each of the fragments. So I want to find VA and V sub D. What type of problem do you guys think this is? What should we be looking to do here? There it is, momentum. How do we know that's a momentum problem? Well, we're given velocities, right? We're given masses and velocities, and we're asked to find a velocity, right? We weren't giving any information about forces or acceleration, so Newton's law is off the table. We weren't given any information about positions or forces, so work and energy also off the table, right? So this is a momentum problem. Okay, so let's start with our diagram, right? Start with a diagram here. So since this is a momentum problem, let's start with our impulse momentum diagram, right? So I'll start, here's my original ball, right? And this is gonna have, let's call this M sub T for M total, right? This is the total mass. When it's all together, this is 20 pounds, right? 20 pounds of weight, which means we have to figure out, remember, we were told it was 20 pounds, not 20 pounds mass. So we have to figure out the mass later. Plus my impulses, right? Plus my impulses. Well, the explosion is an impulse force, right? But that's going to be equal and opposite on each half. Right? This is going to be, momentum is being conserved. There's no impulsive forces, right? So think about it this way. An explosion is like the reverse of a collision almost, right? So instead of the forces being pointed at each other, the forces are going to be pointed away from each other, right? But to the same effect, right? To the same effect. So we're going to get a net of 0 as my internal forces, right? So there's no internal forces. And we can draw it if we want, right? And do something like that. But these cancel, right? We understand that those are going to cancel. And this has to be equal to my final momentum. And I'll move this out of the way. This is going to have, call it MAVA. We know that if we measure this from some point, that this should be 45 degrees, right, to center. This is going to be 30 degrees, and this will be MB. I'm going to move that back in a second. So we have our diagram. What do we know? What are our knowns and our unknowns here, right? Well, I know the weight of the total projectile. This is 20 pounds. Oh, shoot, sorry. Sorry. I hit unfreeze, and sometimes it does it on one screen, but not both. It's weird. I apologize. So we got this, right? So all I've done is I've redrawn the picture that I was given on the previous, but we know that our impulses, what about the weights there, right? Well, we're going to say that the weight's negligible. The weight's a negligible impulse in this system. So I've got the weight of the total projectile. I've got the weight of the piece for A, right? I've got the weight for the piece B. I know my initial velocity, V1, is 100 feet per second. Right, and I have my angles, which I already put on my drawing, but they were given to us. Move that back up there. So if I write out my conservation of momentum equation here, right? It just tells me that the total momentum of my system, right? The total momentum at the beginning has to equal the total momentum at the end, right? So the momentum of the projectile as a whole is equal to the sum of the momentum of the parts, right? But I can break this down into X and Y components, which is where we're going to go next, right? So let's start with the X direction. Oh, guess I didn't give myself any more slides. That's fine. Let's do X direction. In their X direction, how much momentum do I have to start with? I've got all of it, right? It's only in the X direction. What's that going to equal? It's going to be MA times VA in the X direction plus MB times VB in the X direction. Right, so we can plug some stuff in there. Bless you. 20 times 100 is equal to 5 times VA cosine of 45 degrees. Remember, we're breaking this down into components, right? So this is VA X, this is VA Y, this is VBX, and this is VBY. Plus 15. Well, Dr. D, you didn't do the masses, you just used the weight. Why would you do that? That's not right. You can't do that, right? Well, it's a good point. What if I multiply both sides by gravity? What happens? If I multiply both sides by gravity, I just get back to the weight, right? So mathematically, it doesn't matter, right? I can use the weight because I can just multiply both sides by gravity and throw it in there. Or you could divide each one by gravity, right? And it would be the same thing. So it doesn't actually scale, it doesn't actually change your answer. It takes care of itself in this case. All right, so we don't know VA and we don't know VB, so we need another equation, right? Luckily, we have our Y direction equation, right? Call this guy equation 1 right here. What about the Y direction? Well, I have 0 momentum, right? Because there's no Y direction momentum to start with. And then that's going to be equal to my Y direction components of my other momentum. I can call this equation 2. Right, so now I've got 2 equations. I've got 2 unknowns. I have to solve these, right? You can solve them simultaneously. You can throw them in your calculator. Right? Do it however you like. Use your favorite solution method, right? But if you solve these, if I solve 1 and 2 simultaneously, I get VA is equal to 207.1 feet per second, and VB is 97.6 feet per second. So what is this telling me? This is telling me that the lighter projectile is going to be moving faster. The lighter piece will be moving faster than the heavier piece. Does that make sense to you guys? Does that feel like that would be correct? Gut feeling? That they both started moving at the same velocity, but then when they split apart because it exploded, the heavier one's not going to be moving as quickly, right? Larger particles are going to be moving more slowly, almost half as fast than this lighter particle. Whoops. What's up, Zach?
The VA maybe didn't substitute like that.
So if you want to solve it, right, You either solve one of these for VA or VB, plug it into the other one, get your solution, and then plug that back into the first one, right? So you can solve equation 1 for VA, plug that into equation 2, solve equation 2 for VB, then plug in VB back into equation 1, right? Or you can do, there's a lot of different methods, right? You can use calculator, you can use Wolfram, right? You have any questions on this? Right, this is a straight up conservation of momentum. Yeah, Julian.
Yeah, I'm trying to, wait, how do these go faster in this direction than the original? Does that have something to do with the explosion?
Yes, it does. So one goes faster and one goes slower, right? And it also has to do with how much weight you have, right? So it's more of a function of the fact that you've got a quarter of the weight on that one piece, so it's going to be traveling faster, right? There's just less. You think about it in terms of like the force that you would need, right? Because it's lighter, you can use, if you apply the same force to it, it'll go faster, right? It'll accelerate much faster. The velocity will change faster, so it'll accelerate more. So yeah, that explosive force, that impulse there, even though they are equal and opposite, because one is lighter than the other, it's going to affect the velocity significantly more than the other one.
Yeah, because I was wondering, because I thought maybe the ball's flying and they split off somehow. It said, I'm worried about the explosion.
Right. So if you look at the diagram, right, the explosive force on each one of those is equal and opposite. So it cancels in terms of an impulse, right? Because they're equal and opposite, but right. Right, but the effects are different.
I guess, and I also still trying to figure out why the, I think it's fun, but I guess it's like why use how instead of just mass.
So, all right, so why?
But yes, I should have said instead of mass and.
Right. So what if I rewrote this whole equation? Or what if I multiply this whole thing by gravity, right? Multiply by g, right? So each side, multiply g here and multiply by g here, right? Because it's an equation, algebraically I can do that, right? It's not a problem. So if I do that, because I multiplied through by a constant, what am I left with? The total weight is equal to the weight of A plus the weight of B dx, right? So I'm just manipulating the equation. Instead of dividing out by gravity to get the mass, I've decided to multiply my entire equation by gravity. It's the same concept. You can do it either way. It's not gonna, you'll get the same answer. You're just, because what's gonna happen, right? What's gonna happen? When you end up dividing out by that 20, you're dividing by mass times gravity. So you're dividing the gravity out of everything already. Okay. Any other questions? Thank you. Okay. No other questions? Then you guys can try one. Sounds good. All right, so I want you guys work on your tables with your groups. Brandon or Julian, one of you guys can, if one of you guys could move, that'd be helpful. It says winning team gets to pick who has to explain the problem, but at the end of 30 minutes, we'll just come back together and talk about it. Right. No check, no text, no internet, writing notes and calculators only. Please, here's the problem. So we've got a game of pool where ball A is moving with a velocity v naught. It strikes ball B and C, which are at rest and aligned as shown in the diagram. Knowing that after the collision, the three balls move in the directions indicated, and that v naught is 12 feet per second and vc is 6.29 feet per second, determine the magnitude of the velocity of A, ball A, and B, ball B. So you want to figure out what is VB and what is VA. Yeah. You get 30 minutes. You get as far as you can. I'll walk around.
But these are going to have its influence on movement. So it's just like all of A is y will be transferring it into C and B. Oh yeah, it was after it was. Yes, yes, yes. I was just saying what it was. Active force against A.
So for the initial velocity of A and one six. I think not actually.
Well, we know that it was all A strikes B and C. That is feature circles. And then we know that the end result of BC is traveling 6.2 but I should take it baby steps and work from. we should, we have our notes, should we do a kinetic diagram and?
So we're gonna,
So we don't need that.
if it's momentum, then you don't need that.
Yeah.
Divide that. You need
So,
momentum.
yeah, so there's gonna be negative y direction.
Diagram showing that momentum or impact plus the
Yeah, so really, so,
essentially
B is going down.
impact, the impact force of the collision, and in this case, it was,
Okay, so,
they're all hitting each other.
Yes.
So,
Values that we have, so.
ball A hits ball B, right? The force on the two.
You can solve for either.
Yes, you express the force on the other, or the internal force of the the momentum is conserved, right?
Yeah.
It's all about the momentum remaining on the line. How you guys doing?
I think so. I guess I'm gonna solve the BA prime or BB plug in all that.
Perfect.
So which one you want to do where it's going to solve for BA prime and BB? The initial equal velocity at and I guess you're going to divide by the divide by the full time. I guess that would be
This is the momentum. So, yeah, especially what do you know about the math?
I got.
So they're all, they all same.
I got sine, that's
You get NP1 sort of N.
Here we go.
Then there's no N.
Zero.
Yeah, there it is. I saw that.
It'd be sine.
So it's just, it's like the same. So again, there's something that's very wrong, you know. I know, my dad and dad is that long. It's really fun to say. If you ever get on the old names, really, let's see. So the start is the initial head open, right? So then, the second part, we're talking about the collision, right? So the forces between all these particles through this collision. All forces. Right, so if we look just at A and B, right? Because B and C, they are with each other too. So let's start with A and B. So A and B is going to be force from A and B, which is the same as the force from B and A. You were talking about balls, right? Same thing with B and C. So those are all internal to the system, right? So they don't apply any impulses. So they have nothing. All internal. So this ends up being a conservation of momentum. So all the momentum to start with has to go. You can break it down into X and Y components. So if you know how much momentum in the X direction is forward. That's equal to how much momentum in the forward. What the velocity is. You know the velocity is this. You just need to solve what happens to the X direction. Right, so all of this from this V naught, that entire momentum in the X direction has to equal, because momentum is conserved, it has to equal that total amount of momentum that you have the other thing.
Yeah, it's not important there, but I think it's.
In the X direction, same thing for the Y.
Yeah, I guess that's just like. So we have. So yeah, it's like all I guess. But actual AC is the same as it was.
You guys got 12 and a half minutes left.
Oh, sorry. I understand.
It just makes it. Yeah, that was kind of I think that's sort of. I guess it'll make, yeah, I guess it'll be into.
Nine minutes. 9 minutes.
Yeah, yeah. I'll work on that. This is something I would ask, and then I plug that into here. That skips a step. One and then distribute it to whatever. That's gonna be some dashboard.
More for, I guess another historical problems. So because they say it's 45, the next one.
So Professor,
That's it.
my final answer is, I don't think this is right. Like, BB is equal to 5.78. Then I got A prime equal to 12.11. I don't think it would go faster.
So
I might have plugged in BB wrong, but I feel like it is BB, right? That's a volume. B, right? But
let's see.
I work so long.
All right, check your components for make sure that you're using the signs and cosines correctly based off of the triangles that you have. Yeah. So yeah, you've got a feeling that you should be using that data, but definitely. It's correct, right? Yeah, we got like 4.5 minutes left. Was it?
Original X, like you said, and then we took the angle 7.4 and then we minus 6.9 there. Cosine. Miguel, how you doing?
Closer, but not all the way there. All right, guys, thumbs up. Let's talk about it. Talk about it. So, you guys all had stuff there that was close. You did, but you're all just a little bit off. All right. So we were getting there. All right. So. What we got? Well, we got to draw a diagram first, right? And it's a momentum and impulse problem because as soon as we see collisions, we should always, right? As soon as you see something that's a collision, always do momentum, right? Momentum is always done. It's the best way to handle things that are colliding. So I draw my diagram, right? Draw my diagram here. And I've got my initial momentum, right? MAVA at 30 degrees. Then everything hits. When everything hits, all of the impulses are the same, right? The impulse from A to B is the same as B to A. The impulse from B to C is the same as C to B. Their internal forces, they go away. There's no impulses here. And this equals what? My final state, where I have my system of particles here, right? Where I've got MAVA prime, MCVC prime, and MBVB prime. Right? And I know these angles, they're given to me in the problem statement. So I'm going to start with my x direction here, right? I've got MA V naught in the x direction is equal to MA VA prime sine 7.4 plus MC VC prime cosine of 45 plus MB VB prime sine of 49.3 degrees. Now let me ask you guys a question. They never gave us these masses. So how do we handle that? So we can cancel them out. Why? Right, it's pool. And we're going to assume that this is a fair game of billiards where, all the balls are the same weight. Not like when my dad would put in the fake cue ball that's off-centered mass and it would just curve right into the pocket, right? Which is a true story that actually happened. And it's hilarious if you can manage to do that to somebody, by the way. It is. It's really top notch. Another pool story. When I was in college, my fraternity had a pool table, but we got it on the cheap. And the slate was cracked in one of the corners. So there was a big slope, right? So we had a black hole, right? So as long as you got it close to that pocket, it was going in. It was going in. We're all not really that good at pool now because of that. But, All right, anyway, so we can cancel them out. We cancel out our masses. All the masses are the same. So we're left with just these velocity components, right? Remember, look at this, right? Up here. This is my x component. This is my y, right? So cosine to get v naught x, right? On the top here, this is going to be sine of 7.4, right? That's also positive. This guy down here, right? That's going to be what? That's cosine 45 degrees for C. And for B, we're using this guy down here, right? I'm using cosine of 49. I'm sorry, sine of 49.3. Sine. So I'm left with this, right? I know V naught C. I know V naught. I know VC, but I don't know VA and VB. So I need another equation, right? We can get that from our y direction. So we'll sum our momentum in the y direction. Remember, the key here is what? The key here is that it's that thing we talked about at the beginning of class. The sum of my momentum of a system of particles, the total of is just the sum of all of the momentum of each of the particles individually, right? So the total momentum or the initial momentum is equal to the momentum of all of the particles individually added up. So in the y direction, I've got V naught sine 30 degrees is equal to VA prime cosine 7.4 plus VC prime sine of 45 minus VB prime cosine 49.3. And that's going to give me my second equation, right? I can plug some things in, right? And you'll get, I'll run out of space, but we'll do it right here. Right, so I can plug some things into my x direction equation and I'll get some numbers. Cosine of 49.3 degrees. This is an equal sign. And notice I've written this a very specific way, right? Because this is another way that we can do another method for solving these equations. Right, so those are my two equations that I'm going to solve. Right, and if I solve them simultaneously, what I got 7.42 feet per second and 7.66 I'll double check it right now just to make sure. Yep, 7.48 and 7.65. That's what I ended up with. Whoop. I'll drop the cup. So without getting to see like all you guys work and getting in there, right? What are the major things that tends to lead to errors in a problem like this, right? Fat fingering numbers in a calculator definitely leads to that. Making sure your signs are correct, right? Make sure that you're using the right signs and cosines. Make sure you're using the right positives and negatives, right? Make sure you're looking at your vectors, right? At your triangles that you're trying to describe those vectors with. Does have any questions on this? Doing okay? I don't think we're gonna have enough time to do our activity today, so we'll do it at the beginning of next class, right? And I think that'll be fine. we'll just start off in the next class. We'll play around with this stuff. Or maybe we'll do it at the end. That way it's like more fun at the end of the class. But either way, we'll do it next class. And we're gonna keep going with this stuff. So, because there's still a couple of things I want to talk about. I'm really trying to get through some things so that really trying to get through some things so that we can have that review time on Wednesday next week. Okay, so let me ask you this concept question. After impact, what's true about the overall center of mass of the system of these three balls? Right? So we're talking about this particle system, right? What is true about the center of gravity for it after impact, right? So who thinks, we'll do show of hands, the overall system CG will move in the same direction as V naught? Who thinks it's A? Who thinks the overall system CG will stay at a single constant point, B? Who thinks that there's not enough information to determine the location from this picture? Okay. Well, turns out it's secret option D. No, it's A. Turns out that it's A. So think about it, right? What's going to happen? You think about how in a perfect world, right? You line up your pool shot. This one's V is going to impact A, right? A is going to go off at 7.4. VB is going to move down this way, and VC is up. So this is all moving, it's separating, right? But the center is actually going to move along the vector of the original velocity. The entire system of particles as a whole, if you track the center of gravity, it's moving up into, it's going to stay moving up and to the right. It might separate, right? But the center will move up and to the right. Let's talk about kinetic energy then. Yeah, sorry.
Does the center move with the same velocity or not just in the same direction?
Just in the same direction. We'll talk about how we can figure out velocity for center of gravity when we get to rigid bodies in a couple of weeks. It has to do with the relative velocity of some of the particles that we know. Yeah.
That's because it starts with this and then the ending itself is in the same direction.
All right, so think about it this way, right? Like,
Because what if like the ending is down? Would it?
so the system as a whole, right, it's not moving to start with, right? So because it's not moving to start with, I don't want to do this. Think about like, I don't have a good other example, right? So if you were to line up, you know what I should do? I should do that. I have a little fake pool, like a little toy pool table in my office. Maybe we could use that to do this. All right, but so if I've got like this group, all right, so I got the group of these three balls, right? We'll go back to the picture again. All right, what's going to happen, right? After impact, and I'll draw this out over here, right? After impact, ball A is here, right? Ball B is somewhere down here, and ball C is here, right? So the center of gravity is somewhere here, right? But in the initial configuration, before impact, right, we were here, here, and here, right? And we applied a velocity in that direction. Okay. So think of it this way, right? If they weren't allowed to separate, right, and you hit it, and this was like an L-shaped thing that you hit with the ball, right? That entire system, right, is going to move up and to the left. It's the same deal with the center of gravity here. The center of gravity of these particles is going to move up and to the left because we've applied some velocity in that direction. but it's because it was at rest to start with. And yes, they are expanding away from each other, but we don't care about that as much as we know that the center of gravity has to move along that line of action as applied by our velocity. Question. All right, kinetic energy. We talked about kinetic energy before, right? 1/2 mv squared. Well, guess what? Yes, it's 1/2 mv squared, but if you have a system that's rotating, right, we can talk about rotational kinetic energy as well. Right, so what if I wanted to express the kinetic energy of a system of particles? Well, turns out that that's the same as expressing the sum of the kinetic energy of all the particles individually. So if you look at each of the particles individually, right, and you sum them up, you get 1/2 the sum of MIDI squared, okay? If we do this in terms of my centroidal reference frame like we did before, we get an equation that looks like this, right? So it turns out that the kinetic energy, total kinetic energy, is the kinetic energy of the center of gravity plus the kinetic energy of all of my particles, okay? All right. All right, so kinetic energy is equal to the kinetic energy of the center of mass plus the relative kinetic energy of the centroidal frame. Okay, well, that's great, right? But the principle of work and energy can be applied to each of my particles, right? So my kinetic energy plus, or my kinetic energy plus my work from 1 to 2 is equal to my final energy, right? Where the work from 1 to 2 represents the work done by the internal forces and the resultant external forces Fi acting on Pi. Great. We can apply this to an entire system by adding the kinetic energy of all my particles and considering the work done by all the internal forces. So here's the thing. In this case, just because the internal forces are equal and opposite doesn't necessarily mean that the work of these forces cancels out. The forces themselves cancel, but doesn't necessarily mean that there's no work produced on each body. Okay, because remember, what's work? Work is force times distance, right? The distance that we move because of a force being applied. So potentially I could apply the same force to two things, but get different amounts of work that come out because each one moves a different distance, right? So we can't generally say that they cancel, but if the forces are conservative, right, we went over this, then we can say that they cancel and we have conservation of energy, right? T1 plus V1 is T2 plus V2. Great. Great. We talked about impulse momentum, right? A little bit. Here's our impulse momentum diagram again, right? Here's my momentum plus my impulses. And remember, we've got to discuss this in terms of angular momentum. And that hasn't become apparent why we're going to do that, or why we need to do that yet. But it hopefully will soon. Right, so the momenta of particles at time t1 and the impulse forces from time t1 to t2 form a system of vectors that are equivalent to the system of momenta, right? All right, so let's try one. Let's just do it. Oh, hold on, let me see something. I like this one, but I have a better one. I have a better one to end class on if I remembered to put it in here. Yeah, we're gonna do this one instead. This is a better one. Please hold. Wish I had hold music. You guys can imagine. It would sound like elevator music. Thank you for your patience. Your call will be answered in the order which it was received. This one's better. I promise this one's better. And it stays on theme, too. Stays on theme with what we were just doing, right? More pool ball problems, right? Doesn't count unless you call it. That's a rule. That's the rule. All right, so what do we got going on here? We've got another pool ball problem, right? This one's a little bit more complex, right? We've got a lot more dimensions. We've seen the whole pool table. What's going on? Well, ball A has an initial velocity of V naught, right? Which is 10 feet per second, parallel to the axis of the table. It hits ball B and then ball C, which are both at rest. Balls A and C hit the sides of the table squarely at A prime and B prime, right? So what happens, right? This ball A hits ball B comes down and hits the table at B prime, right? Hits it down here. Same deal. Whoa, no. Ball A then travels on to hit ball C. Ball C ends up here, and ball A ends up against the bumper there, right? We've got a lot of dimensions here. Assuming perfectly elastic collisions, determine velocities VA, VB, and VC. Well, hold on a second. They're asking us to find three things. But as far as I know, we only have two equations, right? We've got momentum in the x direction and momentum in the y direction. So what are we going to do? It's a great question. What are we going to do? Well, let's start with what we know. We're going to break this into pieces. Right? So we're going to start off with the collision between ball A and ball B, right? We'll start off with the collision between A and B. Okay? And I'm going to refer back to this diagram quite a bit, but I want you guys to see something right here on this one. I'm going to consider this right here, this solid line that I'm drawing, right? This is my datum. I'm going to measure everything from the center line of the table. Why? Why? I have dimensions from the center line of the table for everything, right? That's where it just makes it easier for me. Is there a reason other than that? No, you can do it from wherever you want, right? You can measure from down here if you want, right? We could figure that out. We could figure that out. I'm going to start it there, though. Okay, that's where I'm going to measure everything from. Now, I'm going to say something here, right? And if you look at this diagram as is, this is great. And this kind of gives you an entire picture of how the momentum works, right? Because momentum just scales my velocity by the mass, right? So I know in this case that I've got momentum coming in at the x, and I've got some x and y components bouncing off, right? But I need to figure out this in-between part. So let's start with the collision of ball A into B, right? Start with that. And if we start there, right, I can draw my impulse momentum diagram where I'll have MA V naught. Well, they're going to hit, right? And same deal as last time. Because they're going to hit, they're going to offset each other with their impulse. So that's going to be 0 plus 0 is equal to what? Well, after the fact, I've got MAVA prime and MBVB prime. Well, we'll just call it MBVB. Okay? All right, so we'll come back to that in a second. I'm also going to draw ball A into C, right? So ball A is going to now have some mass times velocity, some momentum, MAVA prime. Again, this is going to be 0, right? Why? Because they're going to hit each other. And then after these two collide, we end up with MAVA and MCVC. Okay? So that's it. Right? So that's what we end up with. And these are our, so we're going to do this piecewise, right? We're going to do a momentum equation for A into B, and we're going to do a momentum equation for B into C, right? Why? Well, we know that the final momentum of A right, from part one is what brings us in to part B, right, from part two, rather. Okay, so let's talk about our equations. We'll start with A into B. Let's start with A into B. So what do I got? Well, MA V naught, right? That's an x direction equation. So let's start with our x direction. In the x direction, I've got MA V naught. Everything is moving in the x direction. Then the collision happens. I have no impulses. And this needs to equal MA VA prime. What am I doing here? For some reason, I decided to combine this as a vector equation to begin with in my notes. So let's just do what I have in my notes instead of changing things, and we'll address it. All right, so my total equation is MA V naught is equal to MA VA prime plus MB VB prime, right? That's it. Then I can break this into components, except that the way that I'm going to do this is I'm going to say I have this much in the I direction, MA V naught in the I direction. This is equal to mass of A times VA in the X direction, VA prime X in the I, plus VA Y in the J, plus the mass of B times VB X in the I, minus VB Y in the J. Okay. So what I did was I wrote this in terms of the vectors. Instead of breaking it down, I have my i's and my j's together, right? And that's fine, right? And that's fine for right now. Because there's a reason. There's a reason that we want to do this for right now. Okay. So this is that ball A into B equation, right? This is just, if we wanted to break it into components, we could, right? You take all the I pieces, which is my X direction pieces, and you take all my J pieces, right? Remember, this is I, that's J. I'm gonna call this equation 1. We'll put a red dot there so we know that the red equation is now what we're going to be talking about, right? So that's equation 1 that describes ball A into B. Let's write a similar equation for ball A into C. Well, you're going to see something pretty interesting here. Well, at least I think it's interesting. You guys might. This is equation 2. Now, take a look at this. I have an expression for MA VA prime X in the I plus VA Y prime in the J. I can move this whole equation right into this spot, right? I can do that. And that's what we're going to do. We're going to manipulate that and come up with one equation, and then we're going to break it into components. And then we're going to break it. So combine 1 and 2, right? Oh, there we go. Combine 1 and 2. If we combine 1 and 2, we get MA V naught I is equal to MA VA J plus MCVC I plus MBVB X in the I direction minus MBVB Y in the J. So what does this tell us, right? It tells us that the intermediate step doesn't really matter. It serves to couple these two equations together. They just, the total momentum that we had at the beginning is equal to the sum of all of the particles' final momentum, right? It doesn't matter what happened in the middle, right? It doesn't matter what happened in the middle for this problem. So I'll write this in terms of my I direction stuff, right? Call this equation 3, and my j direction. 0, there's nothing in the j there. MA, V, A, minus MB, B, B. Okay, right, this is the part where we say also that we can get rid of all these, right, because so we'll get rid of all of my masses. Why do we get rid of the masses? Well, we don't need them. They're all the same, they cancel. Now this is all well and good, right? But I don't know VB and I don't know VC. So I need another equation, right? Well, I don't know VBX or VBY, right? So I actually need two more equations because I've got four unknowns here. I don't know VA, I don't know VC, and I don't know the components of VB, right? So I need two more equations. Where are those going to come from? Where are those going to come from? Well, there's two places. The first one is conservation of energy. Right? There's no non-conservative forces acting here. Conservation of energy tells me that T1 plus V1 is equal to T2 plus V2. Well, what do I know? This should be a level pool table, right? So it should be level in the gravitational field. It's at the same height, right? Potential energy is all about height differences or springs. There's no springs and there's no height difference, so we have no potential energy. So the kinetic energy to begin with has to equal the kinetic energy of all the particles at the end. Right? In that case, I've got 1/2 MA V naught squared is equal to 1/2 MB VA squared plus 1/2 MB VB X squared plus VB Y squared plus 1/2 MC VC squared. I'll call this equation 5. Still need one more. I still need one more. Sorry, we're going to go like a couple minutes over. I apologize. So I still need one more. Where is it going to come from? Well, there's one thing that we talked about today that we haven't used for anything at all. And that is angular momentum. We're going to measure the angular momentum of this system from where? From the corner of the pool table. From some point that you pick, that you know what the distance is. It doesn't matter where you pick it. You can pick it wherever you like. So the final equation comes from angular momentum. Which tells us that angular momentum at the beginning has to be equal to the angular momentum at the end, because we have no impulses, right? We have no rotational forces or torques added to this system, right? Okay. Remember, these all go away. Right? All those masses go away. They're all the same. They get canceled out. Okay. So what is angular momentum? What is angular momentum, right? Well, it's the linear momentum times the distance that we are away from where we're measuring, right? Luckily, they gave us all these measurements here. Luckily for us, they gave us all these measurements here. Remember, it's positive or it's negative based on not the distance that it is away, but what the rotation would look like, right? So point A is 2 away from this corner, right? Because we're going to measure everything from this corner. if I'm pushing this way, that's going to cause a clockwise rotation, right? That's going to be negative. So that's going to be a negative angular momentum that we have there. What about particle B? Same deal, right? Same deal. It's going to be pointing down at an angle, it's going to cause a clockwise rotation. Particle C, same deal. Particle A at the end, though, that's going to be positive. It's going to cause a clockwise rotation. We know all these distances, and we can make this happen, right? So this is negative 2 MA V naught is equal to 8 MA VA minus 7 MB VB in the y direction minus 3 MC VC. What happened in the x direction, right? What happened in the x direction? Well, remember, point B passes through the origin, right? That x direction velocity when I hit the wall is 0 distance away from where I'm measuring my angular momentum about, right? So it goes away. We don't have any angular momentum contributed by particle B in that direction. Now I've got 4 equations and 4 unknowns. All right, so you guys have the setup here. I want you to solve this system of equations for participation this week. Finish it up and we'll talk about it at the beginning of next class. Okay? Make sure that you private message me your work. It doesn't have to, remember, it doesn't have to be right. I want to see that you tried and that you made effort. That's what I'm looking for. Okay? So try to solve this system of equations. Right? You can go back to the YouTube channel and rewatch the video to make sure you have them. We have the equations right, but just try to solve. Brandon. That's absolutely fine. What's that? Before class starts on Friday. All right. Sorry I went over, but we're done. But wait, there's more nouns. I know it was heavy today. And now I apologize we didn't get to the activity, but we'll do it at the end of class on Friday because you get to shoot a ball at a car and make it crash into things. So I mean, who doesn't want to do that, right? Yeah. Yeah, I'll be around until 5 today.
Okay. And for homework 2, I realized I didn't submit it, but I did do problems 1 through 11 correctly. I just couldn't get the 12th one right.
Okay, I'll take another look there and see because sometimes McGraw-Hill like doesn't submit things right away. So I'll take another look. And
is there any way you could actually we could go back and look at the homework that we've already done?
You should be able to use it as study attempts. Is it not letting you go in?
I'm sorry, what?
You should be able to go back and look at it as many times as you want.
Okay.
Let me know if it's like blocking you or something.
Because usually it's like black and like I can't click on it, so I don't know if there's like another way to like go.
No, let me look into that in a couple minutes when I get back to my office, and I'll.
Yeah, because a lot of my questions are about the Momentus, so we could like, go through a couple problems on that.
Yeah.
Okay.
I'll have to. Yeah, I'll make. I thought I had it set up so everybody would have study attempts on it, so like you could always go back and check it. But I'll double check and make sure that that's correct.
Thank you, Professor.
Yep, no problem. Easy. What's up?
I'm missing points from a Learn Smart. It was the Learn Smart 3. So I remember you moved that due date.
Yeah.
And so it counted.
I'll have to go back in and check. I probably just didn't update it. But thanks for letting me know. I will check as soon as we get back home. Learn Smart 3. You got it. No problem.
quick question. So that group problem we were doing, I actually got sort of far on that, but then really enough, I had a hard time trying to figure out like how to solve those last two equations for the VB and the VB.
Okay.
Because I tried to solve for like VB over here, which would be like this or this, and put it in this equation, and I didn't see how you're supposed to like, because then you have two VBs. And,
Right, okay, so if you end up with the two VBs, right, what's sine of 49? That's just a number, right? So let's, for all intents and purposes, let's say that this one turns out to be 1 and this one turns out to be 2, just for
okay.
sake of argument.
Yep.
Right, then you've got VB is equal, right, so you got to move them both to one side. So I've got 2, whatever, if we said this is 2 and that's 1, right, then I would just subtract 1 VB from here, right?
Okay.
So you can treat it as, so once you figure out what sine of 49.3 is, right, that's going to give you
Okay.
like, what is it? Sine of 49.3. Such a weird angle to get to. It's like 0.75, right? So you have like 0.75 on one and
I actually solved for it was like
0.128 on the other.